Okay, let us continue the analysis of this particular SRAM cell and trying to find out how do we make the read operation proper. So in the previous video we are talking about the cell ratio is the ratio of W by L of M1 transistor to W by L of fifth transistor. Let us suppose if we actually find out what is the voltage at suppose if I say this is the node voltage X, suppose if you are looking at node voltage X, and if you are looking at this as the cell ratio, this is the cell ratio. Suppose if the cell ratio is keep on increasing, you can see now this is how the cell ratio, suppose if we consider this as the voltage at X point, suppose now this is for a particular dimension of 0.25 micrometer. So keeping the dimensions of all the transistors as minimum dimension with L minimum as equal to 0.25 micrometer, it was found out in the simulation that this is 1.2, assume that this is 1.4, this is 0.8, assume that this is maybe 0.6 so and so, and this 1.2 corresponds to 0.4 volt. Let us assume that the VTH of this transistor is equal to 0.4 volt, that is VTH of NMOS is 0.4, and assume that this is a 0.6 and this is 0.8 and this is 0.2 so and so. So what we are trying to understand here is that suppose if the cell ratio is more than 1.2, if the cell ratio is more than 1.2, you can see if the cell ratio is more than 1.2, the voltage at this node is always less than 0.4. This is 0.4. If the cell ratio is, assume that it is 1.3, then the voltage at Vx is actually less than 0.4. So what is the cell ratio? Cell ratio, as it is mentioned here, that it is the W by L of 1 by W by L of 5. So naturally this W by L of 1 is the dimension of this transistor and this transistor. If the value of CR, or the cell ratio, if it has to be greater than 1.2, naturally the W by L of 5 should be less than W by L of 1. If this W by L of 5 has to be less than W by L of 1, means suppose if you try to relate W by L of 5, as it is said that should be less than W by L of 1. So since we are talking about the dimensions, naturally we know that if the width of the transistor is less, then the resistance of that particular transistor will be high. So then naturally the resistance offered by fifth transistor should be greater than the resistance offered by the first transistor, because we are talking about the dimension. If the dimension is, you can see now we are talking about this dimension should be lesser compared to the dimension of this transistor. Since you're talking about the dimension of W by L of 1 should be more compared to this, then naturally the resistance offered by this R1, resistance offered by this M1 transistor should be lesser compared to the resistance offered by this. So what is the implication of the resistance offered by this is more and resistance offered by this is less? Means now you see now, so you have during the read operation you made both of them as precharge to high and high. If the resistance offered by this is less and if the resistance offered by this is more, you know that you earlier you have stored a value of bit is equal to high, so naturally this is low. So since this is low and the resistance offered by this is very less, whatever voltage that tries to rise here will be grounded to this sooner than the voltage that is being that is, of course the voltage will rise here, because this resistor is bit more, the voltage cannot rise to that extent. The charging time of, suppose if you are assuming there is a capacitor here, if you are assuming a capacitor, this capacitor has to charge to this resistor. Since the resistance value is more, it takes longer time to charge the voltage, but as soon as the voltage tries to rise here, since the resistance offered by this is less, the same charge will be discharged soon, very soon. So earlier you had a low voltage, that low voltage will be maintained forever even though you are turning on this transistor with this as 5 volt. Meaning to say here, if this is the voltage at this X point, that won't rise. Of course that voltage will certainly rise. Suppose the resistance offered by this M5 is less. If the resistance is less, then it rises. If the resistance of M5 is more, then it won't rise beyond 0.4. If it doesn't go beyond 0.4, we know that the transistor here, if the voltage doesn't go above 0.4, then this remains in on condition and this remains in off condition, so that you can able to properly read the value. So in order to ensure a proper read operation, M1 should be stronger compared to M5. So we actually saw this condition. Suppose if this condition exists, then you are in trouble. But for proper operation, M1 should be strong compared to M5. So M5 should be weaker one. What do you mean by weak? Weak in the sense the resistance offered by that should be more compared to the resistance offered by M1. So usually these are the transistors which are used for the creating the memory. In order to have more and more memory locations, the transistor dimensions will be kept as small as possible. That will be kept as minimum as possible. So what they will do is they will keep the dimension of this M5 transistor will be kept as minimum dimension. So this dimension will also matter for the capacitance of this particular bit line. So this bit line should have lesser and lesser capacitance, because this bit line is connected to the external circuitry. So since I want to have a very less load on this bit line, the M5 transistor is made out of very small minimum dimension, whereas M1 width, that is W1, will be made longer compared to the length of the transistor. Suppose if your W1 is stronger, then resistance of R1 is less, so that you can able to meet this condition of cell ratio greater than 1.2. Suppose if this dimension is more, if this dimension is lesser, then you can have a greater value of CR. If the value of CR is greater, you can see the voltage at this Vx will never go beyond 0.4, so that you can able to properly read the values. So M5 will be kept at a minimum dimension, whereas transistor M1 width will be increased, and you are keeping the dimension of the length of the transistor of your M1 should be kept minimum, so that you have lesser R1 value. Since the dimension of this M5 is less, naturally the value of R5 will be more compared to the value of R1. Because if the dimension is lesser and lesser, you are going to have the resistance more, and here since you are increasing the W value, the resistance will be smaller. So this way, even though this is a static RAM, during the read operation we have to be very careful. The dimension of M5 should be weaker compared to the dimension of one transistor, so that you don't have a read upset which will make this voltage to become 1, which should never occur. So for proper reading operation, M5 should be made weaker compared to M1 transistor. Okay, next we will see how do we write a particular value onto this static RAM. So let us again rewrite the same static RAM structure. So I'm going to have back-to-back connected inverters. So I have this inverter here, this is again connected, so this is grounded, this is VDD, I have one pass transistor, I have one more pass transistor, this is my bit line, this is my bit line bar. So this, okay, that's fine. So let me connect. Okay, this is not there. Now you can see the M5 and M6 are driven by the word line. This is M5, M6, M1, M2, this is M3, this is M4. Okay, let me connect this to this, and then of course this is connected to this. This is my static RAM. Of course this is not there. Now I want to write. So assume that the value that is stored is high here. If it is high, then actually this is low here. So you have actually stored a 1. You actually stored a 1. Now assume that you want to write a 0 onto this, because this is the earlier value. I want to write a 0. If at all, if you want to write a 0, this should be made low and this should be made high. You can see now this is made low, that is 0 volt, and this is made 5 volt of VDD. This is made equal to VDD. So it can be any value. So this is also VDD. Now we know that during the read operation we have actually pre-charged the bit line and bit line bars. Now during the write operation, whatever value you want to write it onto that bit, that should be applied on the bit line. Since I want to write a 0 onto my register, which is actually storing a value of logic 1 earlier, I am making bit line equal to 0, bit line bar should be equal to the opposite of it. Now you can see it is 0 on VDD because I want to write a 0 onto this. Now when conditions are perfect, now the first thing is that suppose if you want to write a 0, bit line should be made equal to 0, and then bit line bar should be made equal to 1. Bit line bar should be made equal to 1. Then second one is make word line equal to 1. Whenever you make this word line equal to 1, whatever 0 is there, sorry, whatever 1 was there will get discharged through this, and whatever VDD was there, now we can see this is low. This VDD will not be allowed to rise this because it was actually already low. This was actually low here. Now assume that I had a 1 here. This 1 will certainly be going to 0 through this M6 transistor. If this goes to 0, what happens to this? So this voltage will become 0 volt. This will become 0. When this is 0, this is high, and this, okay, when this is 0 means this is on. If this is on means this will become high. So can you see now you are actually writing the value. Earlier it was 1, now you are actually discharging that, so this becomes 0, and this 0 will make this equal to go to high, so that you are actually flipping the value. So value that was stored was 1, now you could able to write the 0 onto this, so everything is pakka. Now assume that you may have a question that since this is high, can this high make this equal to of course, which was earlier stored as, of course you can see now when this is 1 you had a low. So does this high will it actually make this equal to high? This high is, of course, what I mean to say is the write operation will not be performed by this M5 transistor, because there are two possibilities. This high can discharge to 0, and then this 0 will make this transistor on, this can go to high. You can see the low was there can become high. The other possibility is, because when you are writing a 0, bit line is 0 and then bit line bar is high. Now assume that this is not discharging. Now let us try to see that the voltage which was there low here, can this low become high because of this one? So this is not a possible option, because during the read operation we have assumed that, or we want the M5 transistor to be weak. Here you can see during the read operation, what we assumed was, during the read operation we wanted this M5 transistor should be weaker so that I can read the proper values. Now the same transistor with same register with a weaker M5, if I want to use it for writing operation, if I want to do it for writing operation, since M5 is weaker, since I want to write a 0 onto this high which is there on your BL bar will not rise this voltage from 0 to high. So whatever 0 that you want to write it here will happen from this side, it will not happen from this side. So now since it is low, this whatever voltage high you have has to now discharge. When this discharges, naturally this will go to low. When this goes low, this will become high. The low which was stored will become high now. Now the question is, we are somehow saying that okay, this will going to discharge, because at the time of you make this word line equal to 1, the voltage here is low, voltage here is high. This low voltage is turning on this. Whenever you make this word line equal to 1, this is also on. Now we can see there are two transistors which are on. So what should happen? Okay, what we assume that this one discharges through M6 and goes to ground, so that you can have a proper write operation. Assume that if this M4 is strong, does it mean that it is actually always making this high and it will never go to low state? Meaning to say, the dimension of this M4 transistor should be smaller compared to the dimension of M6 transistor. Meaning M6 transistor should allow the voltage here to discharge quickly than this M4 transistor allowing the charges to come and accumulate here. So that will be understood if we understand a ratio called as pull-up ratio. Pull-up ratio, which is nothing but PR. So PR is nothing but, suppose if I write what is PR is nothing but the ratio of W by L of 4 by W by L of 1. Should be always less than 1.8, again for a specific dimension, specific technology of 0.25 micrometer as the L minimum. It is in the textbook. Now we are talking about what is the voltage at Vy, and what is this PR, that is pull-up ratio. The voltage, if the value of PR is keep on changing from 2, 1.8, 1.6, if it is something like 1.4, this is how the pull-up ratio just go here, and then we are looking at a value which is again 0.4, this is 0.2, and this is 0.6, something like that. So assume that this corresponds to 1.8. So what is the meaning of this is, if the pull-up ratio is less than this, you can see if the pull-up ratio is less than this, what will be this? See now, if the pull-up ratio, if it is if the pull-up ratio is 1.5, are you here? So you are here. What are the corresponding voltage here? It is less than 0.4. If it is less than 0.4, what is the condition of this transistor? This is on. If this is on means, so it will be always keep getting the value of high here. Meaning this if this is high, then this will going to turn on. If this, okay, now once this turns on, so now we had this condition, whenever the ratio of this PR, if the value of PR is always less than 1.8, okay, how do we achieve this value of PR less than 1.8? Because I want to have this PR value should be less than 1.8, means if you can just look at this, so what should be W by L of 4 and W by L of 1? So this always ensures that WBL of 4 should be always, so if you want to have this to be always lesser in value, naturally the dimension of 1 should be greater than the dimension of 4 transistor. Suppose if the dimension of 1 transistor is more than the dimension of sorry, this is not 1, this should be actually 6 here, M6. Okay, fine. So what do you mean by dimension of WBL of 6 should be greater than WBL of 4? This actually ensures that the resistance offered by 6th MOSFET should be always lesser than the resistance offered by the 4th resistance. If at all if you are matching this condition, as soon as you make this, of course, as long as this is low and this is high, if you make this word line equal to 1, if you make this word line equal to 1, then you have M6 transistor as well as M4 transistor, both are on. Since the resistance offered by M6 is lesser, the voltage whatever high you have stored here will discharge sooner because the resistance offered by this is less, whereas since this is offering more resistance, this will not charge quickly. By the time this charges, this goes off. When this goes off, the voltage here will going to always go to 0. This way we can able to properly write the value. So for having a proper write operation, we should have M6 should be strong compared to M4. M4 should be weak one. So how do you make this M6 stronger? Make WBL of 6 stronger compared to WBL of 4, so that you can able to get the value always less than 1.8. If this pull-up ratio is less than 1.8, it is guaranteed that the voltage at this point is always less than the threshold voltage of this one, so that it will be always in off condition, so that you can able to get the value whatever value that you are supposed to write here will be done from this arm. This arm will not actually write anything. This arm of your M5 and M5 and M1 is used for reading the values onto your reading the value from your static RAM. So there are two conditions to be satisfied in case of static RAM. One is that, so you have to maintain a value of CR greater than 1.2, and you have to maintain a value of PR less than 1.8. This is for a particular technology of 0.25 micrometer. Maintaining a value of greater than 1.2 means M1 should be stronger compared to M5. In this case, maintaining a value of PR less than 1.8 is M6 should be stronger compared to M4. So this is M4. So if we maintain this condition, then there will be no problem in reading as well as the writing of the SRAM values. SRAM 7.